look at game theory, some of you may never have, or probably all of you have heard about it, but none of you have never really dug into game theory as a topic. There are deeper topics. This time will not allow us to go through the deeper topic. I'll give you the basic topics. Maybe, I think it's even at the PhD level, where I teach that people are afraid, so they don't select it. You all remember the movie called A Beautiful Mind. Which of you remember that movie called A Beautiful Mind? Who remembers it? Who remembers it? A Beautiful Mind. Okay. People don't watch good movies, that's why. All you watch is cantata. So if you watch intelligent movies like A Beautiful Mind, it was actually acted by a certain man known as Russell Crowe. The same guy who acted a movie called Gladiator. Have you all seen the Gladiator?
Yes, Doc.
Yes.
Yes, Doc.
See your faces, because that one is action. People are dying, so that one you like it. Go and watch the same guy's movie, A Beautiful Mind. That guy was playing the role of a certain Nobel Prize winner, John Nash. We shall talk about that today. So in that movie is a typical example of the origin of game theory. Game theory is a big deal. If you want to run a business, game theory is powerful. Have you seen those who do betting when it comes to football?
Yes.
At first, when they see you betting, it's like you are bad, but these days it's even advertised, isn't it? The strategy to do betting in football and in chess is game theory strategy. Game theory is applied when it comes to the OPEC. I'm sure you've heard about the OPEC. It's used a lot in pricing strategy. So before you cut down your price, you check how much your enemy will cut down their price or the rival. Game theory is actually using games. All games apply some form of game theory, and there are different types of game theory. The object of the game theory is to get an optimal outcome. But in a normal game, you want your opponent to lose. But in game theory, when both of you benefit, is better. It's better for both of you to benefit than for one to benefit alone. And you're going to see that the best outcome in a business game is when you cooperate than to compete. Opposite of compete is cooperate. And you're going to see that. It's a branch of economics, particularly microeconomics. Another branch of microeconomics is industrial organization or industrial economics. It uses mathematics to check the competitive situation among rational decision makers. And it focuses on interactions, not just interaction, but strategic interactions. In war, during the First and the Second World War, a lot of strategy, just like optimization, management science, erupted from the war. But game theory was there long ago. Borel, John von Neumann, they pioneered this game theory. So any competition between players, the players here can be anybody, husband and wife, individual friends, movie actors, movie watchers, car drivers, company managers. Any competition between them where strategic behavior plays a significant role, we are talking about game theory. I want you to watch this picture very carefully. And you will know that the people playing the game are usually the people not playing the game. You will know that. Who do you think is really analyzing the game? Who are those analysts? If you know how to play draft, does any of you play draft?
Yes, Doc.
I normally bring drafts when we are physically meeting. Normally it's in my car. The moment you say that, then I bring it out, then we play one. See this man here? This man. He's really playing the game. That man is playing the game a lot, more than everyone. So what is happening is not what is on the game, but it's what's in the mind. Here of the statement that if you keep watching draft a lot, it gets to a point you get to know how to play, isn't it? Have you seen the video where Canada Japan is playing draft?
No, please.
Well, let's look at it. There are two kinds of cooperative, non-cooperative games. One is a static game, which is simultaneous. One is a sequential game, not static. So sometimes we call it dynamic. And the way you represent it also is different. I want you to look at the keywords there. One player decides once without knowing what the other player has decided. That is static game. So the static game doesn't mean the game is static, but it means that when you play without knowing that the other one has played or not. And the players will anticipate the rival's moves. They know that when they play, they will allow you to play. And so they will assume your move. You can easily use a box to represent this game. And this box is known as a normal form or strategic form. You don't know what the other person is going to do. What you know is that he has made a move or he will make a move. But information is very imperfect. That is a simultaneous static game. Then there's a repeated one, a sequential one. That one is dynamic. So the way you represent it, you don't represent it, you represent them using decision trees or using decision trees or diagrams. That's what I use for these ones. So you represent them with things like this. Things like that. That's why you can see that it's dynamic. That's why it's sometimes called extensive form game. The players move sequentially, or they move simultaneously but repeatedly. So we are all doing it at the same time, but we'll repeat. We come to half time and then we continue. We do it over time. And so by coming again, because I know what you did before, I kind of, so sometimes when you look at football game, because I know what they played in the first half, use that to come in now with that in mind. If you're a strategic person, game theory is so abundant in the sport industry. And as you can see, these days, sport industry generates a lot of income. That's game theory. Let's get deeper. Real life. There is a classical example of a game theory known as the prisoner's dilemma. Which one of you has heard about it? The prisoner's dilemma. We're going to use the prisoner's dilemma to explain the basics of game and the nitty-gritties of game for you. Which of you has heard about the prisoner's dilemma? Once again, cantata and amore. Albert, where did you hear about it?
I think they use it a lot in like cop movies where they are trying to play the two suspects against each other to try to get them to confess.
Good. In investigative journalism and in psychological policing, this is used a lot, when you want people to actually confess. Because the only thing is that sometimes when the policeman does not get you to confess, he can't keep you for 24 hours because of the rule of the habeas corpus. So he has to make sure you confess. And therefore they play a game between you and your partner. Not knowing that, because the thing is that if they keep you and you don't confess, they have nothing against you, so they gotta let you go. And this is like duopoly pricing, not Stackerbeck oligopoly, not kinds of oligopoly. It's a duopoly pricing. Let's say you want to look at pricing between Pepsi and Coke, or you have used car transactions. All of them you can exhibit prisoner's dilemma about it. So let's try and get deeper into the prisoner's dilemma. What is a prisoner's dilemma? In a prisoner's dilemma, we have two suspects. They are not jailed. They are only what? They are not jailed. They are what?
They are suspect.
They are suspect. Hussein and Chia. Hussein and Chia. Both of them have been accused of jointly, together, committing a crime. I've underlined jointly for a reason. And the moment they caught, in fact, even before they were caught, you know, in the criminal world, they normally tell themselves, don't route on me. Have you heard of that thing before? Yechiwa.
Yes, Doc.
What did they add? Yechiwa. What? When you are caught, you don't know me, and me too what?
I don't know you.
I don't know you.
I don't know you. I don't even know your family. I don't know anything about you. You are dead when you are caught. I am dead when I'm caught. And this is something the blood covenant about it before they start the journey. Sometimes they'll let you drink your blood and that kind of thing. So they have promised each other that they will not rat on each other, that they will not confess if ever they are caught. Every one of them is trying to minimize his jail time too. But in order to convict them, the police will have to ensure that one of them will confess. They are separated. No information can pass between them. They are allowed to think for 1 hour. And they are allowed to sweat so that they would want to leave that premises. And then a policeman with some file in front of him comes and dumps the file there. And here is the situation. If neither of them confesses, the prosecutor will be unable to convict them of the crime, and each will receive 1 year jail sentence. Have that in mind. So here you are, you got to identify some key things. I'll come to that. If we say confesses and Chia doesn't confess, then we say we'll go free. And Chia will receive 15 years prison sentence. On the other hand, if we say two does the same thing will happen. But if both of them confess, then each will get an intermediate 6 year sentence. If either of them confesses and the other, on condition that the other doesn't, that one will go scot-free. Each suspect must decide once, and once under these circumstances, whether or not to confess. Now there is a conflict of interest here. There is a dilemma. And this situation can be represented in a game matrix. Question is that the information between these two guys, is it perfect or imperfect? And why do you say that? Is it perfect or imperfect? Quickly, these are the beginning things. Albert.
it's imperfect because typically they are separate, so you don't hear what the other person is saying in real time to make your informed decision as well.
Perfect. Now, there are certain things to note when it comes to game theory. And the kind of questions you normally get is what I'm about to ask you here. Determine the strategic environment. Always got to determine the strategic environment. Got to determine who are the players, what are the strategies, what are the payoffs. So let's start with number one. Who are the players? Who are the players in this question? Solomon. Who are the players?
The suspects, and then the police officer.
Police officer is not a player here. Who are the players? Simon. Simon. I normally use this to know those who are paying attention.
I'm paying attention, Doc.
So tell me, who are the players?
So the players are those who.
Jerry, who are the players?
No, please, Tria and the other person.
Husseini.
Husseini.
You know, when you don't know, and some, because you can open the microphone, you can now say the answer into the air. But when you have to open it, you raise your hand, isn't it? So let me see if you'll be raising your hand. So who are the players? Emily. Yes, sir.
Okay. Yes, Doc. Doc, that's Fuseni and Chia.
Okay. You always write the one that comes first. Nobody should copy anything. You always write the one that comes first. And the one that comes first comes from the storyline. And you see that Husseini was mentioned first. So it is Hussein. Number two, what are the strategies? There are two major strategies you must always identify. What is the first strategy? Raise your hand and tell me. Eugene, what is the first strategy?
So the strategy, if they are expecting that either of the suspects would confess by either of the suspects will confess.
No, Albert, what are the strategies? Albert, Kofi. What are the strategies? Albert, what are the strategies?
Oh, okay, sorry. I was trying to unmute myself. It wasn't allowed. Yeah, so the strategy is to disclosure of information. So if Fuseni discloses information or he gives away Tria, he may be able to go scot-free, or he may have a plea deal and he will be allowed to go. So I think the strategy here is disclosure of information.
Gary, what are the strategies?
Doc, so the strategies are one, I confess and have my jail sentence reduced. I have my jail sentence reduced.
Fuseni?
Doc, he said,
Are you Fuseni or Chua?
I am Fuseni.
So you're a criminal. The moment you said I was wondering whether you are part of it.
Okay, sorry. So the sense that Fuseni confesses and have his jail
Strategies.
Yes.
What are the strategies?
confession against no confession.
Exactly. So the strategies are not confess and then confess. Always find this. This is a basic questions. The strategies are either going to be 2 or 3 or 4, but they are either that. Confess or not confess. Those are the strategies. Eugene.
Doc, please, is it the way I mentioned it, is it because of the way I mentioned it, or because I said either of the suspect has to confess, and that is the strategy?
You are talking plenty. And you look like you weren't sure what you're saying. The strategies are usually a word or 2 words. It's not a sentence. So let me go back here. Okay, in case you've forgotten the storyline. This is it. Now I'm coming back here to show you some numbers. So now when I ask you, next question, what are the payoffs? Now the payoffs are going to be things you gain or things you lose. Things the players are going to gain or things the players are going to lose. So in this case, what are the payoffs? Or what is the payoff? Albert.
Okay, so I think the payoffs are 4. One of them is freedom for one person. The other is 1 year jail sentence for both of them. The other is 6 years for both of them. And the other is 15 years for 16 years for one person.
But I don't want the details.
Sorry?
You are giving the details, but I don't want the details.
Okay.
Is the
so freedom or jail time?
Payoffs are what? Jail time.
Or freedom?
You said of what?
Jail time or freedom?
Well, it's still jail time. You can be jail. You give the jail time of, right?
Yeah.
You can be given a prison sentence of 0. It's still jail time.
Yeah.
Yeah. As for freedom, you and I walking, we are the ones with freedom. The thought that you are even arrested itself is a negative payoff. So the payoffs are prison sentence. Got to think through all of this. Okay, next question. You should put these things, you should be writing them on your books, in your books. No, because of certain things that will be happening very soon. Now, the next question you will get is at the top here. Represent the 2-player game in a matrix form. That's what you normally told. Represent this game in a matrix form. And anytime you are told to represent the game in a matrix form, you do something like this. Something like this. That's what you do. The players are usually on the far left. One player is here. Okay. And so because that one player is there, you call it Pussy. Another player is at the top, and you call it what? Chair. And each player will have a strategy. Will have a strategy. Will have a strategy. If the strategies are 3, we'll have a strategy. Okay. We'll have a strategy. Okay. If the strategies are 3. In this case, the strategies are how many? And what are they? Don't confess and then confess. Okay. Don't confess and confess. So don't confess comes first. So when you go to say, you do don't confess, DC, and then confess, C. If you go to chair, don't confess, DC, confess, okay, C. And then you try and identify the payoffs for each one of them. The payoffs are supposed to be under. Okay. So let's start with the DC. When they both don't confess, please remember the role player is the player 1. The player 1, the player whose name comes first is the player 1, which is the role player. Then the column player is the one whose name comes second. Okay. The strategies are what I've given you. If you, according to the story, if there is don't confess, what will be the exact payoff for that? Emily.
Look, they each get 1 year.
Don't confess.
Yes.
Get 1. Eugene.
Don't confess is 15.
It's 15. Okay. Now we have a tie. We have a problem. One of them is lying, actually.
Yes, I am lying.
Good. So remember, the storyline is that if they both don't confess, they don't have enough to convict them. They don't have enough information. They only have the fact that they committed a crime, but they don't have enough. That is why in the criminal world, going to tell on or rat on someone is considered a very big problem. Your entire family can be wiped away. So if we say we'll get 1, and then Chia will also get 1, you put them like that. If we say she confess, and Chia, if we say does not confess, that's this one here, and Chia confesses, what will we say get? Oh, by the way, the first number you write is for the role player, and the second number you write is for the column player. So this one, let me use a different color here. This blue one is for who? This blue one is for who?
Husseini.
Now, when you come to this second one, where Hussein is not confessing, but Chia is confessing, what happens? What will be the payoffs here? The Hussein value will come first. And what is the value?
15.
Remember, Hussein is not confessing, so Hussein will get 15. Now Chia is confessing, so Chia will get what?
0.
It is the same thing that applies here. So what will be the payoffs here?
0.15.
0.15.
Very good. Very good. You remember the numbering. And then if they both confess, what is the payoffs?
6.
Representing this alone is 4 months from the story. Your ability to represent itself is a skill. I'm about to do a test very soon. So that payoff also for the utility is critical. So this is a representation. We say Chia. You can see that I've deliberately used colors to indicate which number is for which player. Representing this. This representation is known as the normal form or the strategic form. So what does this mean? Watch it carefully. What it means is that if Chia doesn't confess, we are here. And Fuse confesses, we are here. Okay, so it means that Fuse is going to get 0 and Chia will get that. Next question. So we explained everything. If Fuse confesses and Chia doesn't, Fuse gets 0, Chia gets nothing. Okay. If both confess, both will get 6. If both don't confess, they will both get 1. Now the thing is that, which one do you think is good for them? Which one do you think is good for them? Okay, let me go back here. That word good will come to the meaning of that word good. Which one do you think is good for them, Simon?
When they don't confess.
Sorry?
When they don't confess and they get the payoff of 1-1.
Good. Why is that not feasible? Why is that not feasible? Why is that unrealistic? because of the tendency to cheat. Write it down. Because Fuse knows Chia's name, and Chia knows Fuse's name, and they know themselves. Even if the person is your friend, the way human beings behave is a different ballgame. Even though they've sworn among themselves, they will not do anything. Now, we are going to look at something known as dominant strategy. We are going to check, and this is another question here. It will be asked the question, does each player have a dominant strategy? That's a question. Does each player have a dominant strategy? What is a dominant strategy? What is a dominant strategy? A dominant strategy is a strategy you will stick to no matter what the other guy does. Write it down. It makes you understand. A dominant strategy is a player you will commit to. Okay? It's a kind of the strategy that you are going to stick to it. It doesn't matter what the guy does. If the guy runs, if he flies, if he walks, if he calls, you decide that you are going to call. That's your dominant strategy. You committed to playing it without even knowing what the other person is going to do. Whatever they do is irrelevant. That strategy is your optimal strategy. Now listen, if one particular strategy dominates all other strategy, it is a dominant strategy. It is not just a dominating strategy. It is a dominant strategy. It's not a dominated strategy. It's a dominant strategy. So we're going to talk about a couple of things very soon. A dominating, a dominated, and a dominant. A is 3. B is 9. C is 3. And D is 4. Which of these A, B, C, D is a dominating strategy? Which of them is a dominating strategy? Come on, raise your hand. Come on, raise your hand. Anytime you're talking about the word dominating, it means that you have two things in mind. Which of these is a dominating strategy? Albert.
So I'd say the number 3 because it recurs the most.
No, I'm just talking about them in terms of numbers. Where bigger is better.
Oh, okay.
Take your time before you answer this one. Because by you saying okay is irrelevant, because you said okay doesn't mean you answer.
It has the highest value.
Who can tell us?
Dog.
Which of them is dominating strategy? Raise your hand, please. Eugene.
Yeah, the dominant
Dominating.
here, dominating is 3.
No, that's wrong. Go and think again. Emily.
Doc, 9, because it's the largest.
No, that is not a dominating strategy. It's not just a dominating strategy. Simon.
Nine.
Emily, you remember when we started, I said, have you guys eaten?
Yes, Doc.
A dominating strategy is a strategy that has a bigger value than another one. A dominating strategy is a strategy, you should write it down. Don't listen, just write. It's just one that has a bigger value than the other one. So which of these is a dominating strategy? Which of them? It's a strategy that has a bigger value than the other one in terms of where we are talking about value, not cost, not loss. So a dominating strategy is the one that has a bigger value than the other one. 4 is bigger than 3. So D is a dominating strategy because it's bigger than one of them. A and C are not dominating. 9 is also dominating because it's bigger than 4. But it doesn't make 4 not dominating among this set. Even though 9 dominates 4 and strategy B dominates D and B dominates A and B dominates C, D also dominates A and C. So 4 and 9 are both dominating. Now listen carefully, which means that which ones are dominated? Which strategies are dominated among A, B, C, D here? Which ones is the opposite? Emily.
That would be A, C, and D.
Perfect. A, C, and D are dominated. The same D and B are dominating. So which of them is both dominated and dominating? Which of them is both dominated and dominating? Eugene.
For D.
D. Which one is dominant? Which one is dominant? Eugene.
9. B.
B. So B is dominant because it's the one that is the most of all dominating. So the dominant is the most of all dominating. Is the one that is the highest of all. Pay attention. We just started. Game theory is exciting, but the moment you lose the foundation, you are gone. Anytime you identify a game and you check the strategies, and each player has got a dominant strategy, we have already arrived at something known as the Nash equilibrium. We have arrived at the Nash equilibrium. And that is what I told you about the movie called A Beautiful Mind, because John Nash was the guy. We have arrived at the Nash equilibrium simply because each player has got what? A dominant strategy. In other words, that player is going to stick to whatever he has. He doesn't just have a dominating strategy. Don't worry. They both have a dominant strategy. They both have a dominant strategy. They both have a dominant strategy. That is why once they both have a dominant strategy, none of them is going to stop playing that. So I'll just walk you through there. Now let's take this example. If you look at this chart I've just drawn here, it is for which player? Is it for player 1 or player 2 that I'm actually going to analyze? And you're going to tell me why you gave the answer. This chart, this strategic form, this normal form I've drawn, is the attention on player 1 or the attention is on the player 2? Albert.
Look, it's on player 1.
Why?
Because you've noted it in the same color, so it's all in red. And they are the first numbers. You also indicated that when the column vector is the one that comes first.
Why is player 1 the focus here? That's a question. You're not explaining it well. First of all, it's not the column vector that comes first. Emily.
Not because the table is showing the player 1's payoffs.
That's it. The table is not showing any payoff for player 2. So obviously, we are not interested in player 2. Okay, now let's focus on player 1. And player 1 has got a strategy called T and a strategy called B. Which is the dominated strategy here? Which is a dominated strategy? We know the payoffs in each. Which is a dominated strategy? Remember, I'm not talking about the payoffs. I'm not talking about the inside. I'm talking about the edge, the strategy itself. Simon. Which is a dominated strategy, B or B?
So it is B.
Good. Why?
Because B has a payoff of 0. which is the most dominated strategy?
Reason is bad. Because when I give you a different number, you will get lost. Why is B the dominated strategy? Okay, if B is a dominated strategy, T is what? If B is a dominated, T is what? Simon.
So T is the dominant strategy.
No, you are wrong. If B is a dominated, as you can see here, it means that T is a dominating. Is the dominating. We are comparing two of them. But also, since there are only two, that T also it becomes the dominant. But what makes B the dominated? That was a question I asked. And she says, because one of the payoffs of B is 0 compared to the payoff of T, which is 1. And 1 is bigger than 0. But that is not all. At the same time, B has another payoff of 4, which is less than T's payoff, which is 5. So in both payoffs, B has a lower value. That is why T dominates B. That is why B is dominated. So if I was looking for an equilibrium, I'll cancel B because B has been dominated. It's an approach known as the iterative elimination of strictly dominated strategy. We'll come to that. Eugene.
Doc, please, not to drag the class back, but then when we transition to this part, I got lost a bit from when we moved here.
Are you asking a question?
Yes, please. I am pleading to get a bit clarity because I am struggling when we transition to this table from the previous explanation that you were given.
I always told you that whenever you are drawing the table, you do something like this. Okay, the player 2 is always at the top, the player 1 is always on the left. I also told you that you always have strategies. Always, you'll be given a strategy. In this example, you have a strategy of left and right. Okay. In this example, you have a strategy of top and bottom. Okay. Now you have some payoffs allocated to each strategy. You were told that the payoffs for P1, player 1, the payoffs for player 1 is 1, and then 0, and then 5, and then 4. Okay. I can also generate a payoffs for player 2. I can have the payoff for player 2 to be 6, 4, 2, and then 1. I've just given the numbers without even thinking about it. So when I'm looking for player 1 strategy, player 1 strategy are the numbers that come first. Okay. So the strategies are these. These are the strategies, top and then bottom. That's player 1 strategy. Player 2 strategy are left and right. Now, if I want to know whether this strategy top, okay, dominates this strategy bottom, I just have to check the values for top here. The values for top here. The values for top, I'll just check it. And you can see that when I check the first number 1, it is bigger than the bottom value, which is 0. So in this case, T is winning. But I need to check all of them for that row before I can conclude whether T is dominating. I go to number 5, I check number 5 against number 4. I can see that T is still winning. B is still losing. Okay? Since these are the only numbers there, I can conclude that T dominates B, and therefore B is dominated by T. Does that make sense?
Yes, please.
Now let me go to player 2. So for player 2, this guy is the dominating guy, and therefore the dominated strategy is this. When you go to P2, you're going to compare this number 6 and this 4. Okay? Because remember, you're looking at left and right. You want to know whether left is a winner or right is a winner. So you check the first numbers. Left is 6 for player 2, and right is 4 player 2. Which number is winning? 6. And therefore, which strategy is winning there? Which strategy is winning there?
Strategy C.
Stop.
Stop.
Which strategy is winning? I mean, left and right. Which strategy is winning?
Left is
Left.
winning.
The left though.
So it's a left strategy that is winning, but you need to add this one to it to be sure whether left is truly the dominating. So you come to the other two numbers. One of them, left is having 2 and right is having 1. Which one is winning?
Left.
Left.
Left is winning. And so since in both scenarios, left is winning, left becomes the dominating and the right becomes the dominating. So when you come to realize that a strategy is dominated, okay, and in this case, if I were to ask 2, that 2A, between right and left, which one would you go for? What do you think 2 will go for? Between left and right, what would he go for?
To go for left.
Left. So left becomes his dominant strategy now. It doesn't matter what this guy does, he's still going to stick to the left because left is winning in all angles. That's why he doesn't care what player 1 does, he's still going to stick to the left. The left becomes his dominant. He's not leaving it. Now you ask player 1, 2, player 1A, between top and bottom, which one do you think is going to be taken?
You always take top.
Yeah. Suppose that player 2 switches to the right. Which strategy will player 1 still be taking? Suppose player 2 switches to take this one. Which strategy do you think player 1 will be doing? Is it top or bottom?
That's still top.
Still top. So he's not leaving his top. Therefore, he has a dominant strategy. Okay, player 1 has a dominant strategy. I can kill this because you see, the thing is that now that T is dominating B, it can go. Now that L is dominating R, it can go. So both of them have got a dominant strategy. Therefore, the two dominant strategy will create something known as a Nash equilibrium. The Nash equilibrium is an equilibrium where everybody is stuck at where he wants to play. Nobody is moving. You know that sort of thing when you are playing draft and somebody is just moving the akuruma on the center lane, going up and down, going up and down. Whatever you do is going up and down. You know that sort of game. I don't care what you do. I don't care. I'm just going. I'm just doing what I'm doing. That's it. That's it. So know the difference between dominant. So that's what we mean by which is, I was just digressing to use this to explain to you what a dominated strategy is. In this case, as you can see in this example, T dominates B. So B is dominated. B is dominated. Okay. So here B is a dominated strategy. Now let's go back to our days. Okay. Question. What is the dominant strategy in this prisoner's dilemma? Do you think that Husseini has a dominant strategy or he doesn't have a dominant strategy? You can tell me. Do you think Hussein has a dominant strategy or not, Eugene?
Yes, he has.
Explain.
So he has a dominant strategy because he in he has an option to not confess and then hope that the other person doesn't confess, and then they get a year term each. However, you cannot predict for Chia, so he has a dominant strategy of confessing and getting a 6 and hoping that the other person doesn't confess or also confesses and then also gets a 6. So I believe the confess, the confess would be a dominant strategy for Husseini.
Well, guys, I hope you all understand. So when you look at it, you see he's going to get 1 or 0. Which one will he go for? Don't confess. He will do don't confess. Because when he does don't confess, he will be, sorry, in this case, the jail sentence, smaller is better. The smaller is better. This one is not where you want the payoff to be more. Here, you want the payoff to be less. So it's like, it's a negative value, so you want less. You don't want more jail. So instead of going for 1 year sentence, you rather confess to get a 0. Instead of going for 15 years, you rather confess and get 6. So whichever way it is, he's still going to be sitting and stuck at confess, because the thing is that he still gets a smaller sentence. What about Chia? Chia will get 1 or 0. And the only way to get that 0 is to confess, because you get a lower sentence. Chia will get 15 or 6. 6 is better sentence than 15. The only way to get that 6 is by actually confessing. So Chia is also going to what? Stick to his confess. You say is also going to sit in his confess. Okay, I've done the explanation here for both of them. So this is regardless of what the other person is at, both of them are going to stick to the confess. So yes, each player has what? A dominant strategy. Now, when 2 players have a dominant strategy, what have we arrived at? What have we arrived at?
At the Nash equilibrium.
We have arrived at the Nash equilibrium. We have arrived at the Nash equilibrium. So now we go to the next question. And the Nash equilibrium, there are parts. Okay? And the first one is known as pure strategy Nash equilibrium. There's quite a number of them. Okay? Like I said, I love this topic. I think next time I'll teach more of this. So pure strategy Nash equilibrium. That's the first and the easiest one. Okay. The pure strategy Nash equilibrium is the first and the easiest one. What is that? According to John Nash in 1951, okay, a strategy is said to have a pure strategy Nash equilibrium if each player is satisfied with her choice, given what the other player is doing, he doesn't care. It is a solution that will appeal to both of them. It is sustainable. He's going to stick with it from all the players are choosing their best strategy. As long as that player is concerned, that strategy is the best. He's not going to move away from it. That is the pure strategy Nash equilibrium. There is another one, another Nash equilibrium, which is known as mixed strategy Nash equilibrium. There is another one. There is another one, which is known as the sub-game perfect Nash equilibrium. Then there's a final one, which is known as the Bayesian Nash equilibrium. The Bayesian Nash equilibrium. Of course, we will not get a time to do those last two, even this one. So, in this case,
Doc, the third one is that sub-what?
Bayesian Nash equilibrium.
Sub-game perfect.
Sub-game perfect Nash equilibrium. People do thesis all on game theory alone. Very, very powerful thesis work. I have some thesis, PhD thesis on game theory, beautiful. Okay, so now that you understand what a Nash equilibrium is, I have some questions for you that will open your mind. A dominant strategy equilibrium is always a pure strategy Nash equilibrium. True or false? True or false? True or false? A dominant strategy equilibrium is always a pure strategy Nash equilibrium. True or false? True or false? True or false? To be honest, I wasn't asking you a question. I was actually giving you a statement, and then everybody thinks that. So write it down. Yes, a dominant strategy. As long as you have a dominant strategy, I have a dominant strategy, you have arrived at a pure strategy Nash equilibrium. Full stop. Number two, iterative elimination of strictly or weakly dominated strategy. These are the approaches we are going to be using now, okay, to arrive at the Nash equilibrium. And when I say Nash equilibrium in this context, to arrive at the pure strategy Nash equilibrium. The first approach you will use to arrive at the PSNE is called the dominant strategy. That's the easiest. The second approach we are going to use is known as iterative elimination of strictly dominated or weakly dominated strategy. We'll look at that. And then the final one is the best response strategy. We'll look at that as well. All of them are done in that kind of order. Okay? You do all of them using the order. So if you try the dominant strategy, it doesn't work, use the IE, SWDS. Okay? If that one doesn't work, you use the BRS. Okay? And you're going to try all of them. So let's start with the first one. Let's go to the prisoner's dilemma. What is the pure strategy Nash equilibrium in this prisoner's dilemma? Who can tell me? You've done it many times. What is the pure strategy Nash equilibrium in this prisoner's dilemma? No. What is the pure strategy Nash equilibrium here? Jerry, Albert.
Doc, confess for Husseini and confess for Chia, getting them 6-6.
Perfect. That's it. That's it. Do that. So the strategy is confess. The payout is 6-6. You will understand why they should eventually get 6 years, 6 years. Why you ask 6 years, 6 years, and 1 year, 1 year. Which one is better?
6-6.
1 year is better.
1 year, 1 year, 1 year.
The guy is not here. You see, when people are not here, and they come in once in a while, that's when you know very well that.
Doc, I'm here.
The people that are talking, that are answering, that are asking, they are the ones here. Okay, when you are not here, it shows. You don't raise your hand again. All right. So the question becomes, why didn't they go for the 1 year, 1 year? I just need brain. I'll tell you the strategy, the answer later. But why do you think they didn't go for the 1 year, 1 year?
No. Please, because that is not feasible.
What makes you know that is not feasible?
Because there's a likelihood that one will betray the other. And so that cannot easily be achieved.
Good. That second point is what I buy. It's called the tendency to cheat. It's because of their tendency to cheat that ended up here. And the police know. Because everybody wants to confess and get the 0, whilst the other will get the 15 years. This guy was trying to confess. Not knowing that this guy too was trying to confess. That's why they ended up 6-6. Now, if this Shia guy had not confessed, then Husseini would have gone for the 0. And Husseini would be free. And Shia would have trusted him for life. But he would have deceived him, as his name sounds. That's why. It is that tendency to cheat that leads to it. Now, this is a pure strategy Nash equilibrium. What kind of equilibrium is this? We'll come to that. So the pure strategy Nash equilibrium is to confess. Okay, before we continue, let me quickly teach you another concept, and then we'll bring it back to the prisoner's dilemma. Because when I ask you a question, I'm asking you all of these peripheries around it. Number 1, Pareto efficiency. Please, it's a little bit tricky, so pay attention. When we say that an outcome is Pareto optimal or Pareto efficient, what does that mean? It means that there is no outcome that Pareto dominates this very outcome. There is no outcome that Pareto dominates this outcome. I'll give you 2 examples for you to appreciate it. Now, can an outcome of a game be better than the other outcome? Can an outcome of a game be better than another outcome? Let's say that you take this outcome. And of course it can. Let's say you take this outcome. This outcome is O. And what are the payoffs? The payoffs are 7 and 8. The 7 and 8 are outcomes. What does that mean? it means that 7 units of utility for the player 1, because the first number is for the player 1. And then 8 units of utility for player 2. Okay, that's good. But if you take this outcome and then you take this second outcome, which is O prime, which one has got bigger elements? Which outcome has got bigger elements generally?
The O. The O.
The O. The O has got bigger elements. But do the bigger elements, are they all of them bigger than the O prime?
No.
No. So between O and O prime, which player is doing well but not doing too well? Which player is doing well but not doing too well?
Player 1.
Player 1.
Some of you are silent. Are not talking. So you can see that in the first instance of O, player 2 actually dominates. Isn't it? Because he has 8. He has 8 from there. Player 2, 8 dominates O, actually would have dominated O prime. Okay, let me ask you. O actually would have dominated O prime if O prime has what number? O actually would have dominated. We call it Pareto optimal or Pareto dominated O prime. If O prime had what number? Tell me.
If O prime had a number less than 7.
Okay, by that you mean you are talking about only player 1, isn't it?
Yes, please.
So you got to be specific. Yes. If O prime or if player 1 in O prime has a number lower than 7, then we would have said that O strictly Pareto dominates. Watch the words. Strictly. But now, O Pareto dominates O prime, but not strictly. Take note. So Pareto efficiency means that you are better off, but then you are not making someone worse off. That's Pareto optimality. Your country is better off by producing the greenhouse gas effect, but you're not making the world bad place for what you're doing. So that is Pareto efficiency. That is, social welfare. But where you do something, but what you're doing is to benefit yourself, but making the other look bad, that is not social welfare. That is not Pareto optimality. That is not Pareto efficiency. So we can say that O Pareto dominates O prime, but not strictly. Not strictly. So we can say that it would have been better if this value here was 6, then we would have said that O strictly Pareto dominates. And as it's now, if Pareto dominates, but it's weakly. It's weakly. Take note. You don't understand. So let me ask you a question. Can a game have more than one Pareto optimal outcome? Can a game have more than one Pareto optimal outcome? You have a game. Can it have more than one Pareto optimal? I mean, if you check it. Absolutely. Okay. Why? And the reason is because if all the payoffs, okay, of 2 outcomes are the same, neither will Pareto dominate the other. I can give you multiple examples. Suppose you have this. You have 2 and 4. Okay. You have 2 and 4. Okay. You have 2 and 4. You have 2 and 4. You get it? If this one is A and B, and this one is X and Y, would you say that any particular strategy Pareto dominates the other? No.
No.
So if all the pairs are the same, then neither Pareto dominates the other. So yes, a game can have more than one Pareto optimal. Because you don't Pareto dominate me in any way, then I am Pareto optimal. Because your Pareto optimality is defined, or is defined by nobody being bigger than you, nobody Pareto dominating you. But if you Pareto dominate somebody, but another person Pareto dominates you, you are not Pareto optimal. Guys, are you with me? Very good. Next question. These are just tricky questions. They're not the ones I'll ask you. Question: does every game have at least one Pareto optimal outcome? Does every game have at least one Pareto optimal outcome? Is it that you are thinking, or you don't know, or you are not there?
No, I think.
Of course. Yes, Jerry.
I think yes.
Explain.
Because in every game setting, you have a strategy dominating the other, or you have a strategy being dominated by another.
I mean, the previous question alone should guide you, right?
Yes.
Must we have at least one?
Yes.
The previous question, yeah, and the example I just gave must answer that. Of course, every game has to have at least one Pareto optimal outcome. Why? Because in order not to be Pareto optimal, it has to be dominated by another. It has to be dominated. For you to say that I am not Pareto optimal, then somebody must dominate you for you to be not Pareto optimal. If all of us are not being dominated, then obviously we are going to have a Pareto optimal. We are all going to be having Pareto optimal. Okay. Now let's go back to the and this is a beautiful thing. The prisoner's dilemma we just looked at. I asked you the question that eventually they all chose confess, isn't it? And got 6 years instead of the 1 year that would have benefited them. Why? And the 6 when you check carefully, it's not Pareto optimal. The pure strategy Nash equilibrium was confess, which led to the 6. But when you check, that is not Pareto optimal. It doesn't have Pareto efficiency. Let's go back and see. Okay, this is a table. Take this one here, which is confess and not confess. Okay. This 1 year is better than 0. Okay. This 1 year, sorry, this 0 is better than 1. But this 15 is, what do you call it? Is better than that. So this guy, let's pick this guy alone and see who is better than it. Or let's say that, is it better than everybody? Because for you to be Pareto optimal, it means that when you compare you with everybody, nobody dominates you for you to be Pareto optimal. So we're going to compare this guy. This guy dominates it with 1, isn't it? This payoff here dominates it. What about this one? This one too dominates it with that. What about this one? This one too dominates it with 1 thing. So this guy here is not Pareto optimal. The same thing with this guy. This guy here is also not Pareto optimal because there is another outcome that Pareto dominates it. Are you guys with me?
Let's go.
No, don't be happy to you.
So now let's check this one. Is this Pareto optimal? No.
No.
You can tell me why. Is this Pareto optimal?
It's no, because
No.
there are other options that are better than that.
Once I mention the option, don't say the other.
So that is don't confess, don't confess.
Don't confess, I've done what?
So it is no, because if
Looking as though you are lying in a bed. That's it.
I'm not lying on bed, I'm not feeling okay.
No.
So when Fusaini decides to confess and Chia don't confess, that one would have been optimal for Fusaini. rather than the 6-6, which is confess.
Jerry, you're going to say something?
I think that's it. I was just saying that over here, lowest is better. So you have don't confess better, which is dominating the 6-6. Confess.
Good. So technically speaking, when you look at it carefully, you can see that 1 year jail sentence is better than 6 years. So this 6 is not Pareto dominating. But now let's go to 1-1. Is this Pareto optimal? Is this Pareto optimal? Abbott.
Yes, Dr. Tis, because the best options out of all the payoff
Is what?
options. It's the best payoff option amongst all the options.
Are you sure it's the best?
In terms of the pairs, yes.
Are you sure?
Yes.
Is it Pareto optimal? That was a question I asked. Simon.
No, because individually, Husseini would love to have no jail sentence, as well as Chia. So the optimal for each of them would have been 0 and 0. That is confess.
That is confessable. Are you sure that is confessable? Why is this not Pareto optimal?
So I'm coming again. So it is not Pareto optimal because for Husseini,
Because there's an outcome that Pareto dominates it.
yes, which is 0.
It may not be the other one, but then it may be the other element.
Yes.
And once there's another element that Pareto dominates it, full stop. It's not Pareto optimal. We know it's not Pareto optimal. We know that this one is also not Pareto optimal. But at least we know that this one is a pure strategy Nash equilibrium. This is a PSNE. But unfortunately, even though it is an equilibrium they will get to, it is not Pareto optimal. That is what we saw. It is a private welfare, but it's not a social welfare. It's a private welfare. It's not a social welfare. A social welfare is something that is Pareto efficient, Pareto optimal. So you can do something that will privately benefit you, but will not benefit society. So that light you put in front of your house is not helping anybody on the street. It's helping you alone. It's a private welfare. It's not a social welfare. Let's go back. So the question was, the reason why the pure strategy Nash equilibrium fails to be Pareto optimal is that in games there are externalities, and it's true, that the players fail to internalize. For example, if you produce a car that is polluting the environment, you're supposed to actually be allowed to pay for the cost of pollution of the environment. But you don't. When you pay for the solution, then it means we are internalizing that externality. But when you don't internalize the externality of your bad thing, because what you've done is that you have disbenefited society by polluting the environment. It's not social welfare, it's private welfare. But when you're allowed to pay for everybody for what you've done, then I'm saying, when you're allowed to pay for it, then you are willing. That is when that, even though it's Pareto, it's Nash equilibrium, it's not Pareto optimal. So for it to be Pareto efficient, you got to share the resources. So we go back to the prisoner's dilemma game. Is there a Pareto optimal outcome in the prisoner's dilemma game? And this is a prisoner. We've already analyzed it. It says that all but one outcome is Pareto optimal. Okay, the 6-6 is not Pareto optimal. Did I say that they were Pareto? Yeah, the 6-6 is not Pareto optimal. That one is not good socially because it's strictly dominated by 1-1. We know that. But then, from what we've indicated, the 1-1 is Pareto optimal because there is no other thing that dominates it. I think I tweaked it. Because when you take the 0 and 15, the 0 and 15 is only beating this guy in one way, isn't it? When you take the 15 and 0, the 15 and 0 is beating the 1, 1 in one way. And when you take the 0 and 15, the 1, 1 is beating it in one way, but not in both ways. For you to be Pareto optimal, okay, for you to be Pareto optimal, no outcome must Pareto dominate you. And this 1, 1, no outcome Pareto dominates it. This 0, 1, no outcome Pareto dominates it. This 15, 0, no. I mean, you beat it in one way, but not in both ways. And once it's not in both ways, then once you can't beat me, then I'm a king. That's why it is. But when it takes 6, because 1, 1 beats 6, 6 fully in all angles, that is why we say that 6, 6 is not Pareto optimal, and the rest are Pareto optimal. So, in fact, the prisoner's dilemma is one of the rare situations, and there are games like that are representing the prisoner's dilemma. It's one of the rare situations where we say that there is no Pareto optimality for the equilibrium. The equilibrium alone, the pure strategy national equilibrium alone, is not Pareto optimal in the prisoner's dilemma. Put it down. The prisoner's dilemma question is a question you can answer in 5 minutes, whilst the others will struggle in 30 minutes. So that's the point I just made. That's the paradox of the prisoner's dilemma. The pure strategy national equilibrium is the only Pareto inefficient outcome. All the others are Pareto optimal. It's the only one that is Pareto not optimal, or Pareto. Whether it's Pareto suboptimal or Pareto non-optimal, if it is not Pareto optimal. But I mean, it's Pareto inefficient. I mean, you can look at a game and you can quickly tell that this one is a prisoner's dilemma style. So the best outcome would have been confess, but because of the tendency to cheat, they end up confess. So now, question for you. Which of these pay off is a Pareto optimal outcome in these 4 games? So let's take the first one, left, right, left, right. Okay, so let's start with this outcome. Is this outcome Pareto optimal? Now remember, bigger is better here. Unlike the prisoner's dilemma, where smaller is better. Is the outcome I've selected, is it Pareto optimal? Albert?
Yes, Doc, it is.
Explain.
It is because when you compare it with the right on the column, it beats it 1, 1. Right, so it's 1 compared to 0, 1 compared to 0. So in that case, it beats it on both parameters. When you compare it to the other one as well, it's 0, 0. So
okay, next one. Next one I'm circled. I've ticked. Is it Pareto optimal?
No.
This one, is it Pareto optimal?
No.
This one, is it Pareto optimal?
Yes.
Good. This is an exam question. So these 2 are Pareto optimal. Let me just show you. That's what I've shown here. So those are the only 2 that are Pareto optimal. Let's go to the next one here. The first one, 2, 1. Is it Pareto optimal?
Yes, it is.
Yes, it is.
Is this Pareto optimal?
No.
No.
Is this Pareto optimal?
No.
No.
Is this Pareto optimal?
Yes.
No.
It is. It's dominating.
No.
There are 3 of you who are not talking, and I'm watching. 2, 1, and 1, 2. Is any of them Pareto optimal?
No.
Both of them are Pareto optimal.
Both of them.
Is any of them Pareto optimal?
No.
2, 1 is Pareto optimal. 2, 1.
2, 1 and 1, 2.
Who is saying 2, 1 is? Is 2, 1 Pareto optimal?
Yes.
Yes, Doc.
Is 1, 2 Pareto optimal?
Yes.
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 No, both of them are
No.
Pareto optimal.
Nobody is, some people are lost.
Both of them are Pareto optimal.
So guys, you
No.
got to understand these principles. Okay, they are Pareto optimal. And the reason why they are Pareto optimal, okay, is because there is no, what do you call it? There is no body that beats them in both ways. And you can see that this guy, even though it's 2-1, this guy beats it on the right side, but he doesn't beat it on the left side. So because nobody beats it on both sides, this guy is Pareto optimal. This one too, because nobody beats it on both sides, it is Pareto optimal on their own. So these two are Pareto optimal. Let's circle the next Pareto optimal outcome. Let's go to the next one. This one here. First one, is it Pareto optimal?
Yes.
This one, is it Pareto optimal?
Yes.
Hey, which one is Doc second that I can see? Okay. Yes.
Emily.
Okay, Doc, I thought we had to raise our hand to be called. I see we can just talk.
That's what I'm saying. Is it Pareto optimal?
Yes, it is.
Is this Pareto optimal?
Yes.
Yes, Doc, they all are.
Is this Pareto optimal?
Yes.
Who is confused? Who's confused? I don't think anyone of you is confused, right? So clearly they are all Pareto optimal. None is Pareto dominated by anybody. And as long as you are not Pareto dominated, you are Pareto optimal. Let's go to the last one. -1, -1. Is it Pareto optimal? Careful.
No.
-1, -1. Is it Pareto optimal or not?
Yeah, yes, Doc, it is.
Somebody says no.
No.
Somebody say yes.
No.
Is it Pareto optimal?
It is. It is.
No, it's not.
Is this Pareto optimal?
No.
Doc, yes, it is.
Negative one.
So let me start with the no. Explain why you say no. For you,
So when you check,
you know it already. So it's not like when I'm asking you before you are thinking about it.
No, we are not think. So the negative one is not Pareto. The negative one is not because both get how am I going to say, like the negative one cannot, if you compare it to, let's say, the one in the column beside it, it is dominating the -4. Sorry, the -4 is dominating it, and then the 0 is also dominating the other -1. So it is not.
It is.
-4 is less than -1.
Negative one.
Yes, it is less than negative,
So
but then it is
-1
not.
dominates -4.
Yes,
No.
And then
it is. It is Pareto optimal.
He still says no.
I
Yeah.
said no because when you look at the
But you are supporting him, eh?
column, we have 0 there, and the 0
You are
dominates.
supporting him, eh?
Yes,
You are
Doc.
supporting him. Okay, go ahead.
So that was it right now. So how you know?
And what I think there are zeros which are dominating the -1, and that's why I think it is not the dominant.
But if the 0 if the 0 dominates the -1, the -1 also dominates the -4. So I think that is Pareto. But the -4, 0 can also be
But when you look at the other column,
No,
the
see,
other
look
column,
at the next column. You see, you move from -1 and then you compare it to that 0, right?
Yeah,
It
yes.
improves, right? But then the other one it's bad, like from -1 to -4. It is not optimal at all. If you compare it to the other one to the column below it, the -4, 0, you see, it also improves from -1 to 0. But then the other one, it is bad, like from -1 then to -4, which is bad. You
I
see,
think we are analyzing them independently. We are comparing them independently. So if you compare the elements in C, as was indicated, -1 is less than 0. So is the 0 with the D is better. But when you go to the top, -1 is better than -1. So relatively, you realize that that is a Pareto optima. But the 0 and -4 can also be an optima against the other.
Just look at the table on top of it, where we had the 2, 1, and then the 1, 2. It's the same instance here.
Yeah.
So in
what is Pareto optima? Can somebody explain to him what is Pareto optima here?
So the Pareto optima, when the outcome dominates the other outcome, but sometimes as it was indicated that
Not
the fact that
the other way. When no what?
Doug said,
when no what?
when no outcome.
Huh?
When you are
Doug, when there is no outcome, that's Pareto dominates
That's it.
That
is the definition you have to give him before you explain. Because if you don't have that definition, it's not when you dominate somebody, no. It is when no outcome Pareto dominates you. So when you analyze that thing, you have to ask, is there any outcome that Pareto dominates this guy? Here. Is there any outcome that Pareto dominates this guy? Here.
So DC.
No.
Take this one, take this one, take this one, each one of them. Ask together, not one, but one on one. In both angles, is there any outcome that Pareto dominates this? Like the numbers, is there any outcome whose numbers are bigger than this guy in both angles?
No.
Now, you ask yourself.
If we are looking at the outcome as in both, then I understand. But if you are looking at it singularly.
Master, we are not looking at this. Did you ever define singular definition? Why are you saying singular? When we were going through all the others, did we look at it singularly? When we were talking about Pareto situation, did we look at it singularly or we looked at it together?
Okay. We looked at it together.
I need to do this faster. Bra. Did you go to the previous one? When we're going through this, did we look at them singularly or we're looking at them? Why did we say that this one is Pareto optima? It's Pareto optima because these two combined, either of them will not be bigger than it. They will not beat it. This guy, okay, both of them will not beat it. This guy, okay, will not beat this one. In fact, first of all, they are the same. Okay, so this one doesn't beat it. So you analyze all of them, they don't beat it. And that is what makes this one Pareto optima. That is what makes this one Pareto optima. Now you go here, you look at this one here. Okay, this guy, okay, doesn't beat this guy. It only beats it in one angle, but it doesn't beat this guy in all angles. So this guy is Pareto optima. First of all, it's Pareto optima because this one too doesn't beat it. This one, which would have beaten it, doesn't beat it. As for this 0, 0, they don't beat it. So this guy is Pareto optima. You analyze this one. This one is 2, 1. This one is 1, 2. It should have beat it in both ways, not one way, both ways for it to be Pareto optima. As for these two, okay, 0, 0, this guy beats it. Once somebody beats you in both ways, not one way, in both ways, you are no longer Pareto optima. So I come to you, those of you who were defending the thing. Is this Pareto optimal or is not Pareto optimal?
It's not.
Okay, it says Pareto optimal, considering, yes, it is Pareto optimal.
Let me go back here. Is this Pareto optimal or is not Pareto optimal?
It is not.
It's not.
So So this one is not. Let's go here. Is this Pareto optimal or is not Pareto optimal?
It is.
It is Pareto optimal.
What about this?
It's also Pareto optimal.
Now this is representing what? This is like what? You know that this is like the prisoner's dilemma. The numbers have changed, but technically this is like the prisoner's dilemma.
Yes.
If you like take all the negatives and you get appreciation of them, it's like the prisoner's dilemma.
Yeah, we do it.
So those should have been the pure strategy Nash equilibrium. But I mean, if you make it all negatives, this would have been the pure strategy Nash equilibrium. Now who is talking? People, when you are muted, when you are not muted, you don't know you are not muted. All right. So that's it. That's the final one. So all of them are Pareto optimal except the pure strategy Nash equilibrium. You should be able to know all of this. Now let's go to the next one, a zero-sum game.
Doc,
yes?
you made one point. I want to clarify if that is the rule. You said if we take out the negative, then that is a Nash equilibrium.
No, because I know the numbers. It doesn't mean that whenever you take a negative from everyone, that becomes a Nash equilibrium.
No, for that particular cell, that 3-3. Yes. So in an event where, let's say, is it always that those that are non-negative are Nash equilibrium, or like we are considering the numbers only without the signs?
These ones are non-negative, right?
Yes, please. I'm just talking about
it's not a rule I just formed.
It's not a rule. Okay, all
right. It's an understanding. If you understand how a Nash equilibrium works, okay, I mean Princess dilemma works when the Nash equilibrium is not Pareto optimal.
Yes,
but all
please.
the others are Pareto optimal.
Yes.
All the others that are not Nash are Pareto optimal. And only the Nash is not a Pareto optimal. That is a Nash. That is a Prisoner's dilemma. You want to take note of it, take note of it to help. I've explained Pareto optimality. I'm now explaining a zero-sum game. It's simple. A zero-sum game is a game where your one man's meat is another man's poison. That's how we normally say it. One man's meat is another man's poison. When we are playing draft, once you take the thing, once you win, I lose. It's simple. One man's meat is another man's poison. So you get a constant value. Now, it doesn't mean that it's a 1-to-1. That can be 4-to-4. So you lose 4, I win 4. That is still. You win 1, I lose 1. You win 10, I lose 10. That is a zero-sum game. Okay. Poker is a typical example like that. Contract. Okay. One person wins the contract, another will lose the contract. So the question is this: is the Prisoner's dilemma a zero-sum game? Given the understanding of a zero-sum game, is a Prisoner's dilemma a zero-sum game? Is one man meat another man's poison?
But I think yes, to a larger extent.
To what extent, Mother? This one, it is what it is, or it is not what it is. What is to a large extent? Albert.
No, I don't think it's a zero-sum game because it's possible for you to both lose or both win, or one person to win and one person to lose.
Absolutely. There's cooperation. There's cooperation. There's no competition. What will lead to your winning is actually when you are cooperating. Okay. So no, it is not a zero-sum game. One man's gain is not another man's loss. Of course, there is a loss, but it's not exactly another man's loss. Even when one is getting a 0, okay, 0 sentence, and the other is getting 15. Okay. But we got to a situation where both of them are getting 1-1. So one is not losing, one is not winning. In fact, in one of the ones I showed you, one man's meat is another man's poison. You see this one here? You see this one?
First dog.
1 minus 1, minus 1, 1, 1 minus 1, minus 1, 1. That's a zero-sum game you're seeing there. That's a zero-sum game. That's a zero-sum. One man's meat is another man's poison. So usually the numbers in the parentheses, the boxes are the same. Okay. Let's go to key questions. Find the These are the key questions you should know anytime. Find the strategic environment. Always identify the players and identify the players. Check whether the moves are simultaneous or sequential. As long as you are using a box to represent them, it's simultaneous. If you are using what do you call it? Less than, what do you call it? That's decision trees is sequential. You should be able to know how to present the game in a normal form or in a game tree form. I've not even taught you the game tree form. You should be able to know how many strategies does each player have. See the one I've just looked at 2-2 strategies. So you can have 10-10 strategies. Check whether each player has a dominant strategy. Check what it is. Find all the strictly dominated strategies, all the weakly dominated strategies. You come to that. Describe an optimal strategy profile for the game. Use the iterative explanation of weakly or strictly dominated strategy to find the pure strategy of play. Right now, we've just used but all the games we saw some few minutes ago, we'll solve for all of them. We'll check whether they are all exhibiting pure strategy Nash equilibrium. Use the best response. I see. You can use the following to find the pure strategy Nash equilibrium. 1, you can use a dominant strategy equilibrium approach. 2, you can use iterative elimination or strictly or weakly dominated strategy. 5, you can use the best response strategy. These are the 3 approaches you can use to arrive at an equilibrium, at a pure strategy. That's what this question is asking. It's asking you to use this one. Is this game a prisoner's dilemma? You will always get a question related to that. Why is it? Why is it not? Are they Pareto efficient? So if you check it, okay, can they be Pareto ranked? Okay, these are some of the questions that you may get. Is this a zero-sum game? Explain. I just looked at one of them. Check all the sub-game perfect of the game. We are not doing this one. I don't think you can find all the mixed strategy Nash equilibrium, the sub-game perfect, the sequential equilibrium, rollback Nash equilibrium, perfect Nash equilibrium, weak perfect Bayesian Nash equilibrium, unique pure Bayesian Nash equilibrium. Now you can use it to solve the Pono equilibrium in the backward induction to find the sub-game. But all of these ones you will not do for this. But these are all the possible questions you can get. To whom match is given, match is expected. Now, let's go to the iterative elimination of strictly or weakly dominated strategy. It's very, very simple. What is it? Okay, so I've already taught you, but I'm just going to go deep. So let's quickly go through this. I told you about a strategy. So this is a strategy. QU, QU, QU. But this QU is 96. This QU is 64. This QU is 48. And then look at American Airlines. That was a United Airlines. This is American Airlines. You have QA, which is 96. It simply means you are talking about the passengers. Okay? 96,000 passengers, 64,000 passengers a year, 48,000 passengers a year between Chicago and Los Angeles. Every quarter, not a year. So look at it. There are so many payoffs. Okay. You are just going to use an approach known as iterative elimination. So this is called elimination. Elimination of what? Of the strategy. Okay. Please look at United Airlines. How many strategies does it have? Quickly. Single.
3 strategies.
American Airlines, how many strategies does it have? Come on, away.
3 strategies.
Now, when I kill this strategy, how many strategies does United Airlines have?
Still 3 strategies.
Sorry?
No, still 3.
They still have 3.
An American?
2.
They have 2.
Okay. So what I just did is called elimination of a strategy. That's what I just did. But what will make you eliminate a strategy? You can only eliminate a strategy if the strategy is dominated. Keep in mind, if it is dominated. Now, if it is dominated in which way? Strictly or weakly? Now, dominated strictly is where, let's say that you have this is A and this is B. And A is 7 and 2. Okay? And B is 6 and 1. But in the second case, A is 7 and 2. And B is 6 and 2. Now, in the first scenario, is it a strictly dominated strategy? Oh, by the way, which strategy is dominating? Is it A or B? Which is the dominated? The dominated.
No.
B is dominated. B is
Dominated is B.
Who said A? The person has not been followed. Dominated is B. So if you look at this first scenario, okay, first scenario, you can see that B, yeah, the elements are small. So B is dominated. Now, in the second scenario too, B is also dominated. But what?
Weakly dominated.
Weakly. So take note that in the first scenario, B is dominated by strictly because in all angles. But in the second scenario, it is almost fully dominated, but it's not strictly dominated. Now, if this one was 3, would you say that B is dominated?
No.
No. B will not be dominated because B is stronger on the right-hand side than A in that regard. So for it to be weakly dominated, one of the two numbers must be the same. One of the two outcomes, the element there must be the same. Please, you guys understand me?
Yes, sir.
Let's move on. Now, so let's go back here to our question here. If we check this, okay, I'm going to, when we are talking about strategy, I'm talking about strategy 96, strategy 64, strategy 48. If we check it carefully, okay, look at it carefully. 96, the elements are 0. 64, the element is 2. 48, the element is 2.3. This is for United. Now for 96, the elements, again, for the next line, the elements are 3.1, 4.2, 3.8, and then 4.6, 5.1. So let's go to that. So if you check all of these strategies, 96, 64, 48, which of this strategy is dominated? So I pass my cursor through all here. When I say it's dominated, so let's check between 96 and 64. First of all, if you take the first one, yes, Emily.
Not the one that's dominated is the 96.
Okay, so let's check it. So if you take the first one, you can see that in this case, because 2 is more than 0, 64 dominates 96. The second one, because 4.1 is more than 3.1, 64 dominates. Third one, because 5.1 is more than 4.6, 64 dominates. So you can see that since 64 dominates from all angles than 96, 96 is said to be what?
Dominated.
Dominated. And once a particular one, is it strictly or weakly dominated?
Strictly dominated.
Strictly. Now, sometimes the question will ask you strictly, sometimes it will ask you weakly, sometimes it will tell you both strictly and weakly. Once they ask you both strictly and weakly, that one is easy. In this case, it's strictly. So you cancel this line. There's nothing you can do about it. It's gone. You don't even have to look at American Airlines. This guy is gone. Now let's go to this guy. 64 and 48, the first one. Which one dominates? Which one dominates? 64 or 48?
48.
48. The second one, which one dominates?
64.
64. Okay. The third one, which one dominates?
64.
64. So you can see that since this guy dominates this guy in one angle and this guy dominates in one, you can't kill everything. So you leave that. Are you guys with me?
Yes, it's weakly
Yes.
dominated.
Now let's go to American Airlines because now we got to blend the two. American Airlines, if you look at 98, 64, 48. If you analyze it per white, which one is dominated?
96.
96 is dominated fully. Is it strictly or weekly?
Is dominated by 64 fully.
No, is dominated weekly or strictly? That's what I'm asking.
Strictly.
But weekly. It's weekly.
Is dominated weekly?
Yes, weekly.
Yes.
You check both
By 64 strictly.
Exactly. Remember, you
No,
never.
by 48 weekly.
No, why would I want to check 48 when I already have gotten a strictly?
Okay.
Okay.
Once you have strictly, you don't even look at, weekly. So it is strictly dominated. So it's out. So we are left with these four now. At this stage, let's try to use elimination again. So we have gotten 64 and 48. So let's go to 64 and 48. Looking at this first one, which one dominates?
64.
64 dominates. Looking at the next one, which one dominates?
64.
64.
So which one is dominated for United? 48. So 48 is dominated, so you can cancel the whole of 48 here. Okay. We are done. We are now left with one more, few more to do. So we are now left with this. But that one is not in the hands of United anymore. It's in the hands of American Airlines. So American Airlines, okay, this time we are looking at the black numbers. Which one dominates? 64 or 48?
64.
So which one is dominated?
48.
So which one is cancelled?
So we cancel 48.
We cancel 48.
48.
Therefore, our Nash equilibrium is this one. So our Nash equilibrium for this particular game is for United Airlines to fly 64 passengers and for American Airlines to fly 64,000 passengers. And that will yield $4.1 billion. That is the income though. That's a Nash equilibrium. That is a pure strategy Nash equilibrium, which was achieved using our iterative elimination of strictly or weakly dominated strategy. So you should be able to use. So when I give you 10 rows, 10 columns, you should be able to use this approach to still get it. Sometimes you are doing strictly. Now one weekly has come to pass. If the weekly comes to pass and there's strictly, focus on the strictly. But look at the question, because if the question also is asking you to use weekly alone, don't go and use strictly. Okay. Now, so this is it. There's another way you could have used to answer this. And that's the one people normally like a lot. So let's look at that. It's called best response strategy. People love that a lot. Best response. Best response. So that one, you are analyzing them one by one. Okay. I'll tell you something. Let's take, for example, so best response is, let's say United go 96. If United should go 96, and this one you're doing it one by one, but it's so sweet. United is going 96. Which one do you think airline American will go for? What would be the best response strategy for American? If United go this line, this 96, American will have to select based on the payoff. So you're not selecting based on the strategy, but on the payoff. Which one will American go for? Which payoff will you circle? That's what I mean. So in this, the best response strategy, you don't cancel the row, you rather circle the payoff. Albert.
48.
No, you are not catching the strategy. You are circling the payoff.
So that will be 4.6.
No, but 4.6 was for American. You are saying that American has moved 96. United has moved 96. What will American do? Okay. Let me show you one. Maybe you get it. So if United go this 96, okay, this 96, American is going to either go for 0, go for 2.0, or go for 2.3. Which one is he going to go for?
2.3.
So you circle 2.3. Stay there. Now, United go for 64. American will go for 3.1, 4.1, or 3.8. Which one is he going to go for?
4.1.
4.1.
Circle that. American. United go for 48. Which one will American go for?
You go for
5.1.
1.
So you circle 5.1. You are done with American. Now let's go. This time American is rather going. What will United do? So American goes 96. What will United do?
United will go 2.3.
2.3.
Circle 2.3. American go for 64. What will United do?
4.1.
Circle 4.1. American will go 48. What will United do?
5.1.
5.1.
At the end of the day, the Nash equilibrium is the one with the 2 circles. Finish.
Okay. That's much simpler.
It's faster.
I told you it is faster and simpler, but life is not sweet. This best response strategy is the best, but then you may be told not to go for that. You may be told to rather use this one to show and use that one to show. Now, in some of the work, you will see that there will be a big table, but it doesn't matter. Whichever ones will have 2 0 pairs, they are Nash equilibrium. So there can be multiple Nash equilibrium. Now, if you can remember, this iterative elimination gave us the same answer. Do you remember?
Yes.
Yeah.
Give us the same answer. The best response also gives us the same answer. But it depends on that. In fact, the reason why we use the best response is because neither of them have a dominant strategy. So the question was, does either airline have a dominant strategy? No. Well, neither of them have a dominant strategy because when you check it, neither of them has a strictly dominant strategy. And that is what normally will lead to. Because see, the best approach is to use the dominant strategy approach. Imagine that it doesn't matter whatever you do, this is all I'm going to play. This is all I'm going to play. You stick with that. And if you will stick with yours, then we already have an equilibrium. But sometimes the dominant strategy doesn't work. And when they don't have, you either use the IESWD or you use the best response. Okay, all of this I've done it already. We've gone through all this, how we obtained this final answer, and how we broke it down and finally got the 4.1. Then we got a final answer. And then we used this one approach. Okay? And then we saw that. Now let's look at this example. I'm going to just use the best response strategy because you all like that one. Use that to address this. So let's start with player 1. This is example 1 here, G1, and example G2. So for G1, for player 1, we have A, B, and C. And for player 2, you have X, Y, and Z. Using the best response strategy, let's go. If player 1 plays A, what would 2 do?
He has 2 responses.
What would be the best response strategy for player 2?
Dog 5.
5. If player 1 plays B.
3.
No.
Hey, sorry.
Why sorry?
Yeah, it can either go. That it can
3.
either be 4.
Why will it be
4
4?
appears twice.
Yes, the first one to. Okay, sorry.
Emily, we're looking at player 2.
We are going B. We are going B here. And we are looking at what he would do here.
3.
It's 3.
Okay.
It's 3. Yeah, okay.
Please remember, when you are circling, remember what you are circling. You are circling for the player above.
Okay.
Yeah.
I'm doing it for you, but if you're in class, you would have done this. Okay. If player 1 plays C, what would be the best response?
5.
5.
Dog 5.
Settle that. Now let's go to player 2. If player 2 goes for X, what will player 1 do?
5.
5. Good. If he plays Y,
3.
Right.
he plays Z.
5.
5.
What is a dominant strategy? What is a pure strategy in Nash equilibrium?
3-3.
BY.
The BY, which is 3-3. BY, which is 3. Okay, so I want you to do this for me.
Okay.
So if A goes, that should be 3.
When you are done, you raise your hand. In fact, when you are done, you raise your hand and privately send me the answer in the chat. I stand for the next lecture, right? Isn't it? Emily.
Yes,
Dr.
we have
Sam.
an advanced party.
Yeah, it's time. It's time for the lecture. Okay, guys, what's your answer? I want the final answer. Anybody?
But please, there was no equilibrium.
Doc, there's no equilibrium.
I know.
There is
equilibrium.
4-3.
So it's 4-3.
It's 4-3.
4-3.
Yeah.
4-3. CY.
See, those who are not doing the thing well, they will come and say that there's no equilibrium.
4-3.
Go and do it properly. So that's the best response strategy. It's BY. That's it. And that is 4-3. Sorry, it's CY. Did I say BY? CY. The first one is BY. We did that together. The second one is CY. That's a pure strategy. So you can use both the iterative elimination or strictly weakly dominated strategy or the best response strategy to find the Nash. Now that is what you're going to do for some of these things. Then you've got some other ones that you will do. We'll look at some of these next time we meet. But remember the approaches. The approaches are very, very simple. We're going to use those approaches to be able to get your work. So you're going to try your hands on this, work it out. Okay? Try your hands on this is another one. This is another one. This is a very tough one. All you have to do. And then circle it, and then finally you'll be able to know. So some of them I've given you the answers, but just try your hands. All right, we're done. Any question?